In our discussion of the reactions of alkyl halides and specifically substitution reactions, we talked previously about the role or the effect of the nucleophile, the substrate, and the leaving group. In this video, we will see the importance of the solvent as a fourth parameter in the substitution reaction. So let's now see the characteristics, if you like, or the features of the solvent suitable for the Sn2 reaction. And an Sn2 reaction, if you recall, is a one-step substitution mechanism reaction where the nucleophile attacks the electrophilic site in a substrate with simultaneous departure of the leaving group. Again, the two events, the nucleophilic attack and the departure of the leaving group, take place at the same time. So this is once again a representation of the Sn2 reaction. This could be X or L. L or X is a leaving group, of course. Yeah, halides are good leaving groups, as we discussed before when we talked about leaving group ability. So the nucleophile, and of course the nucleophile must have always a lone pair for it to be able to function as a nucleophile. So the nucleophile is going to attack this electrophilic carbon. This electrophilic carbon is electrophilic due to inductive effect, and simultaneous departure of the leaving group takes place, and the product, the Sn2 reaction product, is this substitution product where X has been substituted by a nucleophile. So this is the Sn2 reaction. Once again, nucleophilic attack followed by departure of the leaving group take place at the same time. It's a one-step mechanism reaction. What about the solvent? Obviously, reactions are usually, although not always, but usually carried out in media or a medium that is called a solvent. And of course, the solvent is very important in reactions, as it homogenizes the reaction mixture, it stabilizes reaction intermediates, and it enhances the rate of the reaction. So its role of the solvent in chemical reactions is understood, and it is very, very important. Now, what about the solvent in the Sn2 reaction? What characteristics should the solvent, or a suitable solvent in an Sn2 reaction, should have? What characteristics it should have? Okay, you see, for the reaction to take place in one step, so nucleophilic attack followed by departure of the leaving group, for the two events to take place, then the nucleophile must go and attack quickly. This is a one-step reaction. So the nucleophile attack should be facilitated. It should not be hindered. Anything that hinders the nucleophilic attack in this reaction will slow down the reaction, if not stop it at all. So therefore, the solvent should not hinder the nucleophilic attack. And the solvent can hinder the nucleophilic attack if the solvent is polar and it is protic, which means it has a proton, like in water and alcohol. So alcohols and water are polar protic solvents, which are not suitable for the Sn2 reaction because they hinder the nucleophile by solvation. So let's do that, and then we will see the other type of solvents that cannot do that kind of solvation, which hinders the reaction, and therefore the ideal choices, if you like, of solvents in the Sn2 reaction. So solvents like alcohol, so this is the general structure of alcohol. Remember, alcohols are not suitable for the Sn2 reaction. Here we are showing what alcohols can do and what they can do with respect to hindering the reaction, if you like, or stoppage of the reaction. And then we will appreciate the other types of solvents which don't do this and then facilitate the reaction. So if we have a nucleophile, the nucleophile is supposed to go and attack that electrophilic carbon, as you see, in a fast one-step reaction. Now, if there is a solvent like an alcohol, so this is a solvent, yeah? Alcohol, if an alcohol is chosen as a solvent in an Sn2 reaction, then the alcohol will interact with the nucleophile by hydrogen bonding. So this bond is a hydrogen bond, and therefore the nucleophile will be surrounded by the alcohol, by alcohol molecules, or by water molecules, or by the polar Aprotic solvent molecules. Okay, this hydrogen bonding, or the surrounding of the nucleophile by the alcohol molecules, is called solvation. So therefore, solvents like alcohols and water solvate nucleophiles, and solvation impedes nucleophilicity. Solvation impedes nucleophilicity, which means the reaction will be stopped. The Sn2 reaction will be stopped if an alcohol solvent is used. Alcohol solvents like water, they are also polar. They are polar protic. As you can guess, the term protic comes from a proton, basically a polarized hydrogen atom or a proton. Any solvent that has a proton is not suitable for the Sn2 reaction. So the alcohols and water, also, these are not good. Alcohols and water, these are not suitable solvents for Sn2, for the Sn2 reaction. So the suitable solvents that then would be still polar, but solvents that do not have a proton. Solvents that do not have a proton. So the ideal or the suitable solvents in Sn2 reactions would be the solvents that are polar and aprotic. Polar and aprotic, which means A means not, yeah, so like chiral, achiral, yeah, so not protic, which means they don't have an acidic, no acidic proton. They don't have an acidic proton. So unlike water, you see, water has hydrogen bonded to an oxygen atom, so that hydrogen is acidic because it's next to an electronegative atom. Same thing applies to alcohols, yeah. So alcohols and water are polar protic solvents, which are not suitable for the Sn2 reaction because they solvate nucleophiles. They impede the nucleophilicity of nucleophiles, and therefore they stop the Sn2 reaction from taking place. So the suitable solvents in the Sn2 reaction are polar aprotic solvents. Polar aprotic solvents. Examples are the following. This is acetone. Acetone, it's a solvent that's a very common solvent in the organic lab. So acetone as a reagent, or as acetone could be used as a solvent in this case because acetone does not have a protic, an acidic hydrogen, and therefore it is an aprotic solvent. So acetone is suitable as a solvent. Acetonitrile also, CH3CN is suitable, so that's another example of a suitable solvent in Sn2 reactions. There's also dimethyl sulfoxide. So this is called, or abbreviated actually as DMSO, dimethyl sulfoxide. Dimethyl sulfoxide is an excellent solvent in Sn2 reactions. This is a CH3CN is acetonitrile. Yeah? So acetone, acetonitrile, DMSO, DMF, dimethyl formamide, dimethyl formamide. This is DMF, dimethyl formamide. This is also another example of an excellent solvent in Sn2 reactions. If you notice, these solvents do not contain a hydrogen on an electronegative atom. They don't contain a hydrogen. You see, this hydrogen, for example, is not bonded to an electronegative atom. These hydrogens also the same. They are not bonded to electronegative atoms, and also the same thing applies to acetone and acetonitrile, unlike water and alcohol. So these are polar aprotic solvents. They don't contain an acidic hydrogen, and therefore they will not interact with the nucleophile. They will not, therefore, solvate the nucleophile. They will not impede the nucleophilicity of the nucleophile, and therefore the nucleophilic attack in the Sn2 reaction will be facilitated if a solvent that is polar and aprotic of these examples, any of these examples, and there are actually even more. So a polar aprotic solvent should facilitate the Sn2 reaction. Solvents that are polar and aprotic like water and alcohols are not suitable in the Sn2 reaction. What about solvents in Sn1 reactions? What characteristics or features should solvents have in order for them to be suitable in Sn1 reactions? Let's recall the mechanism. This is the general structure of the substrate with L as a representation of a leaving group. If you recall the Sn1 mechanism is a two-step mechanism reaction, unlike Sn2, which means the two events, the nucleophilic attack and departure of the leaving group, do not take place at the same time. The first step is departure of the leaving group, so the Cl bond breaks, and this breaks a carbocation. As you remember, a carbocation is formed. So this is the carbocation intermediate that's obtained, and then the nucleophile comes in a subsequent step in the nucleophilic attack step to attack the electrophilic carbocation to give the final substitution product. So this is the product plus, of course, L minus overall. So the nucleophilic attack, the departure of the leaving group takes place in the first step. The nucleophilic attack on the electrophilic carbocation intermediate is what takes place in step 2. So this is the two-step mechanism reaction, just for us to remember it, and then we try to predict important features, or if you like, requirements for solvents to be suitable in this reaction. Yeah. So unlike Sn2, if you remember Sn2 reactions, we mentioned, okay, that solvents should be polar aprotic. The solvent in Sn2 reaction should not have an acidic hydrogen, which would then, or through which would then interact with the nucleophile in solvation. Yeah. The solvent in Sn2 reaction should not solvate the nucleophile, and therefore the solvent in that case should be polar aprotic. In this case, here a carbocation intermediate is formed. So any solvent, or a solvent that can stabilize, a solvent that can stabilize the carbocation intermediate would be suitable. And carbocation intermediates are stabilized by inductive effect. They are stabilized by electron donation, if you like. So any solvent that can donate electrons to the carbocation intermediate would be able to stabilize it, and therefore that solvent would be suitable. So, for example, if we take water as an example, water has option with two lone pairs, and then we draw the general structure of a carbocation intermediate. This is a carbocation intermediate. Remember, carbocations can be of different substitution degrees. Okay, they can be also allylic and benzylic, as we discussed before when we talked about the reactivity of substrates in Sn2 and Sn1 reactions. So the water can actually interact with the carbocation, or can donate electrons to the carbocation, and this interaction is a stabilizing interaction. This is a stabilizing interaction by electron donation. So this stabilizing interaction would help stabilize the carbocation intermediate. So this would stabilize the carbocation intermediate. So any solvent that can stabilize the carbocation intermediate should be suitable in the Sn1 reaction. Water, as an example, alcohols are also suitable in this reaction. So therefore the conditions should be, the conditions or the requirements for the solvent should be polar protic. So polar protic solvents are ideal or ideal or suitable in this reaction. So this is what the ideal solvent in the Sn1 reaction should be: polar and protic solvents. Examples are, as given here, examples are water and alcohols. In general, water and alcohols are suitable solvents in the Sn1 reaction because they are both polar and protic. So to conclude here, suitable solvents for Sn2 reactions should be polar aprotic solvents that should facilitate the nucleophilic attack and prevent solvation of the nucleophile, which would happen if protic polar solvents are used in that case. In the Sn1 mechanism or the Sn1 reaction, the solvent should be polar protic. The aim here, or the goal, is to stabilize the carbocation intermediate by electron donation.